Hello. First of all, we are glad to be here in this prestigious event and thank you all for the opportunity to present our work. Providing adaptive traffic routing based on user and network context is an ongoing project that has been under development since 2014 by a research group at Unifax University. My name is Sergio Spinola, and on behalf of this group, I will be the presenter of this work as well as its achievements. As shown in our presentation outline, we will cover the conceptual approach, including a brief description of the context model, as well as the context-aware framework, and also a case study based on an implementation of this framework and experiment that led to some results, as well as development perspectives. Introduction context. We all know that QoS, quality of service, is a very well-studied topic and has quite some effort on implementations applied to different scenarios. The question is that all approaches took only in consideration network parameters and techniques related to traffic engineering. They are all network-centered and the user perspective has not been considered in most of those solutions. We are, in our approach, placing the user perspective into consideration, at least bringing the user into the center in something bigger that we consider to be the context. Problematics. The problematics is that network service providers can't see the user response, as well their reaction to the experiences. The fact is that we are having new kinds of applications, uses and experiences that the network engineer is not even close to be aware. There are plenty of new applications and possibilities that the users are experiencing that involve satisfaction, and some of them are pure emotional. So how to gather those new parameters in order to build context data and use this data to optimize traffic delivery? Our main goals are, in this way, to propose a solution capable of dealing with new complex parameters in order to understand either the traditional network perspective as well as user contextual information to provide adaptive routing. This requires a context-aware framework. Conceptual approach. Our work is based in three main pillars: adaptive routing, QoS, that stands for quality of services, and QoE, that stands for quality of experience. Talking about adaptive routing. Adaptive routing is the capacity of the routing system to adapt its traffic delivery, its routes, and data forwarding paths, flow tables, and so on, according to the traffic behavior, in order to achieve performance. We are able to find out many approaches to accomplish this, such as based on context, based on traffic engineer, based on probabilistic data, based on algorithms, based on routing scheme, based on probabilistic information. Talking briefly about QoS, that's the most well-known and explored approach. And it should be said that should always be considered one of the fundamental parts of adaptive routing approach. It also should be said that it does not describe completely the network environment. Talking about QoE metrics, due to the new kinds of users, of network by users, it's more and more important to understand how the user feels the service. This can be gathered from metrics that are also known, such as MOS, that stands for Mean Opinion Score, or it can be collected from the user behavior within an application. Talk about the context model. What we call context model. It takes into consideration many different aspects of a user, such as his location, time of the day of usage, or even the weekday, the quality of the equipment that is used, if it's accurate or not. For example, we cannot expect the same experience within a noisy environment and bad quality device. We can compare it with a nice and silent environment using a last generation device. Of course, even though they have the same QoS, if they have different equipment and different environments, their experience will be different. All that said, this diagram synthesizes the data information related with an entity, the human factors, the device and infrastructure, location, time, etc. There is a concern about the quality of data gathering. In complex environments, it is also crucial to build filters that will avoid false positives that would make the system useless. This filter is achieved through the quality of context block, as may be seen in the right column. We also choose the JSON as a representation form to represent data. In this example, we are depicting QoS, QoE, and network data representation. It's clear that the readability is favored in this kind of representation. We can see the QoS data, QoE data, and QoE in the network data very clearly. Context-aware framework. The context-aware framework is built in a modular way, and each block may be built independently. Here are the handling, the context model management, context forward management, and flow adaptation. This layer was built in a way that can be extended to OpenFlow. The so-called context controller was named as CARV and is compounded of two main blocks. First block is context approach, and the second block on the right is the forwarding approach. The first one deals with the data acquisition from the network environment and generates context information that will be processed by the context model manager. If a flow adaptation is needed, the second block, named forward approach, will be notified. In the end, a change in flow table will be generated and applied upon the network elements, resulting in new data paths. In a glance, the handler deals with data captured and acquired, and it can interact with external agents in order to achieve that goal, whereas the context model management applies policies and then may eventually notify the forward approach block to apply forward rules upon the specific user traffic. The second block is responsible to create new routes or data paths and feeds the network elements with flow information. For example, by means of a REST API, it will be possible to notify a SDN controller. How? We can see here in this example, we have a HPVAN SDN controller that makes Open vSwitch data available to JSON format and by means of a REST API. It's possible to make gets and puts in this SDN structure. This kind of architecture was followed by CARV implementation. Talking about the case study itself. In this case study, that involves an actual experiment, we used a cloud database called MongoDB with JSON data representation available for context control. In one, NetFilter IP tables plays the roles of the routes. The agent was implemented with a network data collector named the StarTrainit that is capable of generating QoE data, in this case, mean opinion score. In two, the middleware collector gathers the data collected. The context header is then notified whenever a change occurs in user experience. The context header applies the rules, and in this case, QoE is the rule under experiment. After POC reasoning, if a QoE violation is detected, the notification about this violation is sent forwarding approach in 8. In steps 9 to 12, a new flow route is chosen, and in this particular experiment, in step 13, a change in net filter IP tables is required, meaning a new flow queue. In this way, in the general case, a new flow entry would be created and notified to the switch. We can see this graph. The data path here is represented by queues that are quite constrained. This is a scenario with lack of resources. In this situation, we have 4 queues, one with 300, another with 700, another one with 1400, and 2400 kilobits capacity. The left scale reflects the RTP MOS, mean opening score, that's measured from 1 to 5, where 1 is the worst and 5 the better. This is a QoE measuring taken by the middleware agent. At the beginning of the experiment, 3 simultaneous calls are applied and the MOS measurement remains at the top. A few moments later, the simultaneous calls are doubled, and in instant 1, the MOS measurement drops to the bottom line. The context controller reacts, and a new forwarding path is chosen. In this experiment, meaning that a new key is chosen through an IP tables command issued from Python routine. This constraint is repeated just before instance 3 and 5, and the system always responds to a new flow adaptation. Conclusions and future perspectives. Conclusions. After those tests, some conclusions were made. We were able, during this work, to consider a variety of metrics such as QoE and also device with the usage of different codecs. The main advantage of this solution is to deal with the dynamics of nowadays networks. A flexible representation model is also crucial due to these dynamics. That tends to be dramatic. The format chosen, as well as JSON representation, revealed to be very flexible and in line with the same representation adopted in SDN controllers such as RIU and HPVAN. This tends to turn the communication with SDN controllers straightforward. Regarding future perspectives, at this stage of the work, we are continuously working on refinement of the model, as well the definition of new set of rules, such as QC and QD. Currently, our work is done in order to implement forwarding rules applied to SDN structures and this is underway. The RIU controller is one option of choice since it has Python implementation. We are also considering ONUS and ODL as controllers to validate this interaction. And this is a perspective to broaden the variety of SDN scenarios. Thank you very much for your attention.